Hi folks, I want to give you a brief description of how to draw something called a Lewis dot structure. Now a Lewis dot structure is a graphical representation of the covalent bonds between nonmetal elements. Essentially, I'm going to draw our old friend water. A Lewis dot structure is a way to describe how the hydrogens and the oxygen are combined in bonds at these 2 points. Remember, we talked about a covalent bond being between 2 or more nonmetal elements. And we talked about it being a sharing of electrons. So the question arises, can the way they are shared be described? And the answer is yes. It can be described by drawing this Lewis dot structure. There's some fundamental rules for drawing the Lewis dot structure, and they are this, and let me change colors here. 1, first of all, you need to calculate or count the number of available electrons for bonding. So that's the number in the valence shell. And that's the number in the valence shell for each of the atoms involved in a particular formula. Number 2, we calculate the ideal number of electrons to make everybody happy. And that's by following the octet rule, where, oops, there's a little extra E on there. Each element is happy with 8 electrons. So normally we'll just multiply 8 times the number of atoms. The only times we don't do that are when we're dealing with either hydrogen or helium. They only need 2 electrons to be happy, and you know that. So once we have done that, if there is a difference between the two, we subtract the available electrons from the ideal number of electrons. And that tells you how many electrons are shared. However, that's the number of shared, and I'm just going to write a little e here for electron. Electrons, when they are shared, follow what's known as the buddy system. Remember the buddy system if you've ever had to go somewhere as a young child and you had to grab a buddy? Well, electrons do the same thing. They travel in pairs. There's a pair of electrons. So if we take the number we generated in number 3 and we divide it by 2, we'll get the number of bonds that exist between the various elements. So let's just take a look at how this looks like in practice. And I'm going to just erase everything that we have written, and we'll choose a nice blue color for our first example, which is going to be our old standby of water. Water is 2 hydrogen, 1 oxygen, equals 3 atoms altogether. And if I refer to the periodic table, that the numbers at the top tell us the number of available electrons in each of the columns for the elements. And we could calculate that anyway, because we know that this is the first shell, this is the second shell, this is the third shell, this is the fourth shell, etc. And the first electron is in the outer shell. If you're looking for oxygen, would be in the 2s1, and then there's another one in the 2s2. There's another one in the 2p1, 2p2, 2p3, 2p4. So we add all the 4 in the p orbitals with the 2 in the s orbitals, and we end up with the exact same number that's written right here, 6. So you can calculate the number of electrons, or you can look at the number at the top of the column for each of the elements. Oxygen has 6 electrons, and we know that hydrogen has 1 electron. So if we go back to our example that we're working on, and I follow the steps that I outlined previously. And the first one is I count the available electrons. There's my abbreviation for electrons. Oxygen has 6. Each hydrogen has 1. So 2 times 1 for the hydrogen equals 2. Plus 1 times 6, because I only have 1 oxygen, equals 6, equals a sum total of 8 available electrons. Number 2, I'm going to calculate the ideal number of electrons. And in this case, hydrogen each wants 2, oxygen wants 8. There are 2 hydrogens, so I would need 4 plus 8. I would need 12, ideally 12 electrons. So number 3, I will subtract the available electrons from the ideal, and I find out I have 4 shared electrons. And because they share the buddy system, I'm going to divide 4 by 2 to tell me the number of bonds that exist between oxygen and hydrogen. Well, I told you that this was a graphical representation, and all I've done so far is write down a lot of words. So what do I mean by graphical representation? Here's what I mean. I'm going to write down my oxygen, and I am going to put its 6 electrons around it. All right, 1, 2, 3, 4, 5, 6. It's not happy, doesn't have 8. And I will bring hydrogens alongside, and they each bring 1. I can look back at number 3 and see I have 4 shared electrons that create 2 bonds. How can I make that happen? And what I do is I rearrange these electrons. So I will bring this electron closer, and I will bring this electron closer, and I will rearrange some of the other electrons. So it begins to look like this. Oxygen in the middle, and here is a hydrogen with its 1 electron. Here's its hydrogen with its 1 electron, and then 1 from the oxygen, 1, 2 from the oxygen, 3, 4, 5, 6. And then I do some evaluating, and I say, here's 2 electrons for that hydrogen, 2 electrons for that hydrogen, and 8 electrons for the oxygen, with 1, 2, 3, 4 being shared, which is what I want. And so, Mickey Mouse, our water structure, is happy. This can also be illustrated or written in this manner, with a line. And then we can write the unpaired, unshared electrons as well. A bond indicates a pair of shared electrons. That line indicates a bond, and that is a pair of shared electrons. So it can be written either way. That is how you draw a Lewis dot structure. So let's try it with one more example, and then you'll be on your own. Let's try it with carbon dioxide. 1 carbon, 2 oxygen, and if I were to go look at my periodic table and find carbon, it has 4 electrons. Oxygen still has 6. So my carbon has 1 times the 4 electrons equals 4. And the oxygen has 2 times the 6 electrons, which equals 12. We add those 2 together. I have 16 electrons available. And that is my step number 1. Step number 2 would be calculating the ideal. I have 1, 2, 3 atoms all together, none of which are hydrogen or helium. So I'm going to multiply that times 8, which is the number of electrons in the valence shell that makes it happy, which means I need 24 electrons, ideally. I will subtract 16 from 24 to get 8. Electrons must therefore be shared. And then 8 divided by 2 equals 4 bonds. So I will have 4 bonds. Now you remember between the hydrogen and oxygens in water I only had 2 bonds. In this case I will have 4 bonds. So let's try to see if we can write this. I'll write my carbon first. It's a singular atom and so it can go at the center. When I'm building an atom I try to take the single elements and put them in the center and then build around it. Carbon is often at the center, just as a hint. And I will put carbon's 4 electrons around it. Then I'll put an oxygen over here and an oxygen over here, and each one has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I will look and wonder, how in the world can I get 8 electrons shared? Well, what I will do is, first of all, I will take this electron and move it down here, and this electron and move it over here. And then I can actually take another pair of electrons from the oxygen on either side and share it as well. And so what does this look like in a manner that we can actually see what's going on? It will be my carbon in the center with its 4 electrons now lined up on either side, and then a pair of electrons from this oxygen with its 4 other electrons that are unshared over here, and then the pair of the oxygens I moved from this location on this oxygen and then slightly rearranging its 4 other electrons in this manner. But you say you have 4 electrons here, and I can. What happens is that this creates what's known as a double bond. And so altogether I have 4 bonds, which, if we look back over here, is exactly what our little method predicted. And I am sharing 8 electrons, which is also what our method predicted. And let's just take a look at where they are. Carbon has 8 electrons here. Each oxygen, there's 4 over here, and then 4 on the outside, has 8 electrons. And then those that are shared are in these 2 regions. 4 plus 4 is 8. 8 electrons shared, which agrees with this. And let's make it a little bit brighter color for the happy face. Everybody's happy. This is what carbon dioxide looks like. And that's how you would write it. I hope, apart from being very colorful, that this helps describe how to write a Lewis dot structure using a method that's fairly foolproof. And the method was given to me by one of my students who actually figured it out. And I thought it's definitely worthy to be shared, and I don't often see it as clearly explained in many textbooks. Good luck!